Alright, let us consider a scenario. You have just landed in a new city and need to find a hotel. You open Google Maps and it quickly shows you the way, but how does it know your location? It uses a co-ordinate system, a network of invisible lines that form a grid across the earth. Just like Google Maps uses this system to guide you, coordinates are essential in countless fields. Whether in 2D or 3D, coordinate systems are the backbone of how we understand and interact with the world around us. We have divided this video into three main sections. Let's take a quick look at what we'll be learning. In the first section, we'll provide a clear introduction to coordinate systems, including polar, Cartesian, and curvilinear coordinates. In the second section, we'll explore orthogonal, spherical, and cylindrical coordinate systems. Finally, in the last section, we'll briefly discuss the transformation and change of axes. This video is made for the purpose of an assignment on coordinate system presented to Mohammad Zahid Sir, Lecturer, Department of Tripoli, University of Chittagong, presented by Team Not Geniuses, featuring Safia Salim, 24702035, Sabrin Sultana, 24702045, Nabiha Norin, 23702051. Math course 161. Now we are going to start out today's topic, coordinate system.
Here we can see that coordinates are classified into 2D and 3D. In 2D, there are two systems, polar and Cartesian coordinate systems. In 3D, it is divided into Cartesian and curvilinear systems. The curvilinear system is further categorized into two types, spherical and cylindrical coordinates. We all have studied the polar and Cartesian coordinate systems during our 11th or 12th grade, haven't we? Let's take a quick moment to review these concepts. Imagine we need to determine the location of a point P in a 2D space. In the polar coordinate system, which you can see on the left side, we measure the distance from the origin to the point P, which is called r, and the angle theta formed between this line and positive x-axis. Together, r and theta describe the position of P. Now, let's look at the Cartesian coordinate system on the right side. In this case, we move x units in the direction of x-axis from the origin and then y units in the direction of y-axis to reach the point P. Here, the coordinates of P are expressed as xy. To simplify, let's use an example. Imagine a child born in Bangladesh learns to count as ek, dui, tin, and while a child in England learns to count as 1, 2, 3. They are expressing the same numbers but in their own way. Similarly, the polar and Cartesian system describe the same point P but use different methods to do so. So, while the methods may differ, both coordinate systems ultimately guide us to the same destination, just like different languages expressing the same meaning. Similarly, when we talk about 3D, we can visualize the x-axis, y-axis, and z-axis as shown in the diagram. Here we can see a point P with coordinates A, B, C. In this case, A, B, C represent the distance along each of the axes. First, we move A units along the x-axis, then we move B units parallel to the y-axis, and finally we move C units parallel to the z-axis. By following the path, we reach the point P.
In this video, you can see that the 3D axes x, y, and z are perpendicular to each other as defined by the right-handle rule. These planes intersect to form a rectilinear grids. Now, our goal is to understand how a point is located in 3D space. It is not always necessary for the new coordinate axes to form 90-degree angle with each other. In this context, we will explore curvilinear coordinates, where coordinate axes do not have to be straight or perpendicular but can be curved instead.
Now, let's move on to the proper definition of curvilinear coordinate system. As we can see in the diagram above, we can say that u1, u2, u3 are the coordinates of x, y, z, where c1, c2, c3 are constants are called coordinate surfaces. And each pair of these surfaces intersect in the curves called coordinate curves. Here in the diagram, each of the three surfaces represent one of a family of the surfaces generated by different values of the parameter C1. The U1, U2 and U3 coordinate curves of a curvilinear system correspond to the XYZ axes of a rectangular system. Since the three coordinate curves are generally not straight lines as in the rectangular coordinate system, each coordinate system are called curvilinear coordinate systems. I tried to draw curves in 3D. Although it doesn't perfectly represent the curvilinear coordinate system, I hope it helps improve your understanding. Here, even though the intersection might look like points, they are actually curves formed by the intersection of the three surfaces. We can imagine an imaginary coordinate u1 aligned along the x-axis, keeping u2 and u3 constant. Similarly, we can derive u2 and u3 in a comparable manner. Now, let's talk about what a unit vector in the curvilinear system actually is. We know that the unit vector along x-axis is represented as I cap, the unit vector along y-axis is j cap, and the unit vector along the z-axis is k cap. Note that I, j, k are orthogonal, meaning I dot j is equal to 0, I dot k is equal to 0. Now, since we have created a new coordinate system, we also need new tangent vectors. These unit vectors allow us to specify directions in the new coordinate system, just like I cap, j cap, and k cap do for the Cartesian system. Now, let's learn some terms that will help us to understand future concepts more easily. In the diagram, small e1, small e2, and small e3 are the unit vector along the axes. Once we identify these unit vectors, we can define another system of unit vectors called capital E1 cap, capital E2 cap, and capital E3 cap. Here, how they are defined. Small e1 shows the direction where u1 increases along the curve. Small e2 points in the direction where u2 increases. Similarly, e3 shows the direction of increasing u3. This second system of unit vectors help us to understand the orientation and directions in the curvilinear coordinates more clearly. Here we can see that capital E1 is equal to 1 by capital H1 into del E1. Similarly, we can get E2 and E3. Here, capital H1 is the magnitude of del E1. Vector representation in terms of base vector A vector can be represented in terms of unit base vectors E1, E2 and E3, or capital E1, E2 or E3 are the form. A is equal to A1 into small e1 plus A2 into small e2 plus A3 into small e3 is equal to A1 into capital E1 plus A2 into capital E2 plus A3 into capital E3, where A1, A2 and A3 and also small a1, A2, A3 are the respective components of A in each system. Now, let's discuss the concept of an orthogonal coordinate system. Previously, we have learned that small e1, small e2, and small e3 are the unit tangent vectors to the coordinate curves. If the tangent vectors e1, e2, and e3 at a point P corresponding to the coordinate lines u1, u2, and u3 are mutually perpendicular, then the coordinate system u1, u2, u3 is called an orthogonal coordinate system. Alright, we have covered the basics of curvilinear coordinate system. Now, let's take a closer look at all types types of coordinate system that fall under this category.
Let us get introduced to two new topics, which is spherical and cylindrical coordinate systems.
Alright, we have covered the basics of curvilinear coordinate system. Now, let's take a closer look at all types of coordinate system that fall under this category.
Let us get introduced to two new topics, which is spherical and cylindrical coordinate system. But before we dive deeper into this topic, we have to learn something new, which is reference direction. What are the type of reference direction and what are they? Let's start with the easier one, the zenith reference direction. The zenith reference direction refers to a vertical axis pointing upwards, positive z-axis, in 3D space. It is commonly used as a reference for measuring the polar angle theta in spherical coordinates. The polar angle theta is measured from the zenith 0 degree down towards horizon 90 degree and farther below 180 degree, which is basically the positive z-axis and the negative z up to the negative z-axis. Imagine standing outside looking straight up at the sky. The point directly overhead, that's the zenith. In a coordinate system, this zenith direction aligns with the z-axis. It's the vertical axis representing height and is often the starting point when we measure angles in the spherical coordinate system. Let us look at the 3D representation of the z-axis and how does it work. Imagine you're standing at the origin of the three axes. You look exactly above you. That is the zenith reference direction. The second and the last of the reference direction is the azimuth reference direction. Azimuth reference direction measures the direction of a point in the horizontal plane relative to a fixed reference direction. Typically, the reference direction is the positive x-axis or the true north. Azimuth reference direction is a bit different than zenith reference direction. So instead of looking up, picture yourself standing on a flat surface, like a big map, and you look in front of you in a straight line along the positive x-axis, which is usually considered as the north direction. That is the starting of the azimuth reference direction. It is actually about the orientation in a horizontal plane. It tells us where we are relative to a fixed direction. In most cases, the starting reference is north or the positive x-axis. From there, we measure the azimuthal angle moving counterclockwise. For instance, 0 degree might point north, 90 degree is east, 180 degree is south, and 270 degree is west. Now let us again take a look at the 3D representation of the azimuthal reference direction. Starting from the x-positive axis, we are moving counterclockwise towards the positive y-axis, which is the east direction. And when we reach the negative x direction, it is the south. And then the negative y-axis represents the west. Orientation from the positive x-axis determines the azimuthal angle. Now that we have covered the unfamiliar parts, let's move on to our main topic, spherical coordinate system. Spherical coordinate system is a three-dimensional system that represents a point in space using its radial distance, the polar angle, and the azimuthal angle relative to our central origin. In real life, it has a lot of application, namely, it is used for weather forecasting, it can be used for GPS navigations, and it is also used robot configurations. Now let's break down the spherical coordinate system using a figure. We are all familiar with the XYZ axis. Let's consider a point P in the axis. From the point P on the XY plane, we draw a vertical line. And then let's join the origin and the bottom of the vertical line together. The angle that is formed between the positive x-axis and the connecting line is the azimuthal angle. As we already know that the positive x-axis is considered the azimuthal reference direction, right? And then in the z plane, we draw a line connecting the P point and the origin, resulting in the formation of an angle between the second connecting line and the positive zx, which is our zenith reference direction. That is called the polar angle, and the distance from the origin and the point is called the radial distance. Like this, r, theta, and phi are the three coordinates in the spherical coordinate system. So the three coordinates point of the spherical coordinate systems: first, the radial distance r is the distance from the origin to the point. Second, the azimuthal angle theta is the angle between the positive x-axis and the projection of the point onto the xy plane, determining the point's direction around the z-axis. It can be up to 0 degree to 2 pi, which is the 360 degree. Now the last, the polar angle phi, is the angle between the positive z-axis and the line connecting the point of the origin. It can be from 0 degree to pi, which is 180 degrees. Moving on, we will cover the basics of spherical coordinate system, its 3D representation, transformation from other coordinate systems, and then we will end with some mathematical exercises. At first, let's see how do we measure distance in spherical coordinate system. The distance in spherical coordinate system can be derived using the formula from the transformation of Cartesian coordinate system to spherical coordinates. Suppose there are 2 points, P and P prime. Their coordinates be P is equal to r theta phi, P prime is equal to r prime, theta prime, and phi prime. The distance between the 2 points, d, is equal to root over r squared plus r prime squared plus 2r r prime sine theta prime cos phi minus phi prime square plus cos theta prime. So with this, if 2 points and their coordinates are given in the spherical coordinate system, we can easily find the distance between the 2 points using this formula. Now, to get a better understanding of the coordinate system, let's look at the 3D representation of spherical coordinate system. Moving on to kinematics, now we will see how to find out the position vector, velocity, and acceleration in the spherical coordinate system. In the first glance, it may seem really difficult, but it is not. For the position vector r, it is equal to the r, or the radial distance, in the coordinate multiplied with the unit vector r. Then coming on to the velocity, v is equal to r times unit vector plus r theta, unit vector of theta, plus r phi sine theta phi, unit vector. Acceleration, we know that it is the differentiation of the velocity. So when we differentiate velocity with respect to time, we get a really complex formula. But if we can find out the correct differential values and the double differential values, we can find out the acceleration easily using the formula.
The transformation from Cartesian to spherical coordinates involves a redefinition of the coordinate system axis. from the Cartesian axis xyz to spherical coordinates r, theta, phi. Relationships between the coordinates. The transformation is based on geometry. 1. R equal root over x square plus y square plus z square. Distance from the origin to the point in 3D space. 2. Theta cos inverse z by r. Angle between the point and the z-axis. The transformation from spherical coordinates to Cartesian coordinates involves converting a point's representation in a 3D spherical system to a 3D Cartesian system. Transformation formulas given r theta phi. X equal r sine theta cos phi. Y equal r sine theta sine phi. Z equal r cos theta. Now the explanation. Radial component r represents the distance from the origin to the point. This is the scaling factor for all coordinates. Azimuthal component phi determines the direction of the projection of the point in the xy plane. Polar component theta governs horizontal point is from the z-axis. The trigonometric term breaks the position into the components along the Cartesian axis based on the angles and radius. Visualization. Start with the point at a distance r from the origin. Rotate by theta down the z-axis. Rotate by phi around the z-axis in the xy plane. The formulas combine these steps to locate the point in Cartesian space.
Going with the flow, let's look at some mathematical exercise. Let us consider a problem where a point is defined in spherical coordinate systems as r is equal to 7, theta is equal to 120 degree, and phi is equal to 60 degrees. Convert this point into Cartesian coordinates x, y, z, and calculate the distance of this point from the origin in Cartesian coordinates to verify the consistency with the given radial distance. At first, we will write down what we already know. From the transformation of coordinates, we know to transform the spherical coordinates to the Cartesian coordinates, we follow the formula x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So following the formula, putting theta is equal to 120 or 2 pi by 3, which is in radian. Also, phi is equal to pi by 3, that is in radian 60 degrees. We can write x is equal to 7 sine 2 pi by 3 cos pi by 3. Again, further calculating the maths, we get x is equal to 7 root 3 by 4. Next, we have to find out the coordinate y. Y is equal to 7 sine 2 pi by 3 sine pi by 3. We know sine pi by 3 is equal to root 3 by 2. So y is equal to 21 by 4 after calculating. Then comes z. Z is equal to 7 cos 2 pi by 3. Cos 2 pi by 3 is equal to minus half. So z is equal to minus 7 by 2. We now have our Cartesian coordinates from the spherical coordinates. XYZ is equal to 7 root 3 by 4, 21 by 4, and minus 7 by 2. Now let's move on to our next part of the question, which is finding out the distance from the origin. We know the formula in Cartesian coordinate system, which is r is equal to x squared plus y squared plus z squared. So as we already have the Cartesian coordinates, we can just directly put the values in the formula and then we can find out the distance. After calculating, we can see that the distance is 7. So the Cartesian coordinates are 7 root 2 by 4, 21 by 4, and minus 7 by 2, whereas the distance from the origin is consistent with the given radial distance is equal to 7. Our next topic is cylindrical coordinate system. Cylindrical coordinate system is a three-dimensional coordinate system that is used to specify a point's location by using the radial distance, azimuthal angle, and the height of the point from the particular plane. Using cylindrical coordinate system, we can find the coordinates of any cylinder, pipes, or something bizarre that is an hollow inner spiral staircase. Yes, anything cylindrical we see in our real world can be determined by the cylindrical coordinate system. Now let's understand the coordinate system further with the help of a figure. Let there be a point P in the XYZ axis. The perpendicular line on the XY plane from the point P parallel to the Z axis is our Z coordinate. Now connecting the bottom of the perpendicular line to the origin, we get an angle theta with the positive x-axis in our azimuthal plane or xy plane. Interestingly, in this coordinate system, we do not have zenith reference direction or zenith plane because here the zenith plane completely aligns with the positive z-axis. That's why we do not have any need to further complicate it. So that's why we just take the z-axis and the azimuthal reference direction. Let's see what are the coordinates here. First, we have the radial distance r, that is the distance from the point to the z-axis. Coming on, we have the azimuthal angle theta, that is the angle between the positive x-axis and the projection of the point on the xy plane. Then come our height, which is z, that is the vertical position of the point along the z-axis. So with that, we have the three coordinates of the cylindrical coordinate system, namely r, theta, and z. Now, just like the spherical coordinate system, we are going to look at the basics of cylindrical coordinate system with the 3D representation, then we will move on to the kinematics, and lastly, transformation, and then end it with a sum exercise.
The transformation from Cartesian coordinates to cylindrical coordinates involves a change in the coordinate system to better describe problems with rotational or cylindrical symmetry. The relationship between the two coordinate systems can be derived and explained as follows. Cartesian coordinates are defined as x horizontal distance along the x-axis, y horizontal distance along the y-axis, z vertical distance along the z-axis. Cylindrical coordinates are defined as r, the radial distance from the z-axis or the origin in the xy plane to the point, theta, the angular displacement in the xy plane from the positive x-axis measured counterclockwise, z, the same vertical coordinates as in Cartesian coordinates. Now, how the transformation from Cartesian to cylindrical happens. The x and y axis in Cartesian combine into a single radial distance r. The angular position theta replaces the specific xy directions to indicate the orientation in the xy plane. The z-axis remains unchanged. Derivation of transformation equations: radial distance r equal root over x square plus y square. Angular displacement theta equal tan inverse x by y. Now, visual explanation. In Cartesian, a point xyz is uniquely defined by its projection onto the x and y axis. In cylindrical, the point is uniquely defined by how far from the origin it is in the xy plane, what angle it makes with the positive x-axis, and its height.
Now, not to be too detached from the reality, let's see a 3D representation of our coordinate system. In the video, we can see that there is a cylinder where there are three axes mentioned: x, y, and z axis. Considering the top of the line as the point We have tried to show how does the coordinates in the cylindrical coordinate system works and how do we find any point in the Z coordinate system. The vertical line is the Z coordinate and the line joining the vertical line and the origin is the R coordinate, which we also called radial distance. The angle between the positive x-axis and the radial distance r is our polar angle theta. Countless points and their three coordinates r, theta, and z together form a similar structure like cylinder. This is why this coordinate system is called cylindrical coordinate system. Just like the spherical coordinate system, we have gone through the transformation and the 3D representation. Now let's see how to find out the distance between 2 points in cylindrical coordinate system. Distance in cylindrical coordinate system also can be derived from the formula from the transformation of Cartesian coordinates to cylindrical coordinates. So let there be 2 points P and P prime, and their coordinates P is equal to r theta z, and P prime is equal to r prime theta prime z prime. So the distance d is equal to root over r square plus r prime square minus r prime cos phi minus cos theta minus theta prime square plus z prime minus z square. Moving on, we have the kinematics of the coordinate system. Position vector r here is r unit vector r plus z unit vector z. And then vector v is the differentiation of the position vector r, obviously. So the first derivative of r multiplied with the unit vector r plus r theta first derivative multiplied with the unit vector of theta plus z first derivative times the first plus z prime unit vector of z. The acceleration. Acceleration A is the differentiation of v. With that, we get the formula for the acceleration. From the formula, we can see that the second derivative of r, theta, and z are used to find out the acceleration. So lastly, let's look at a problem to get it ingrained in our brains. Convert the Cartesian coordinates x, y, z is equal to 3, 3 root 3, 5 into cylindrical coordinates r, theta, z. We already know from the transformation of Cartesian coordinates to cylindrical coordinates, r is equal to root over x squared plus y squared, theta is equal to tan inverse y by x, and z is equal to z. Now using this formula, we will find out what is r. Putting the value of x and y in the formula, we get that r is equal to 6. Then comes theta. Putting the values of y and x, we get that r is equal to pi by 3. In radians, in degrees, it is 60 degrees. And as we have already said, that cylindrical coordinate system shares the z coordinate with the Cartesian coordinate. So we don't need to find, put on a complex formula to find the value of the z coordinate. Z is equal to 5. So the coordinates of cylindrical coordinate system are theta z is equal to 6, pi by 3, 5. If you want, you can try to verify your answer by again transforming them into the Cartesian coordinates. If you get the same answer, that means that your math is correct. So with that, we have covered both the spherical and cylindrical coordinate system.
Now, the operation of Cartesian coordinates, cylindrical coordinates, and spherical coordinates in vector field. For Cartesian coordinate, it is ax, x cap plus ay, y cap plus az, z cap. For cylindrical, it is a rho, rho cap plus a phi cap plus az, z cap. In spherical, it is ar, r cap plus a theta cap plus a phi cap. Now, Cartesian coordinates in gradient, nabla x f, x cap plus nabla y f, y cap plus nabla z f, z cap. For cylindrical, nabla rho f, rho cap plus 1 by rho, nabla phi f, phi cap plus nabla z f, z cap. In spherical, nabla r f, r cap plus 1 by r nabla theta f, theta cap plus 1 by r sine theta nabla phi f, phi cap. Divergence is a dot product of nabla and a. For Cartesian, nabla x ax plus nabla y ay plus nabla z az. For cylindrical, 1 by rho nabla rho, rho a rho plus 1 by rho nabla phi a phi plus nabla z az. For spherical, it is 1 by r square nabla r square a r plus 1 by r sine theta nabla theta a theta into sine theta plus 1 by r sine theta nabla phi a phi. Lastly, curl of Cartesian coordinates. Nabla y az minus nabla z ay x cap plus nabla z ax minus nabla x az y cap plus nabla x ay minus nabla y ax z cap. For cylindrical, 1 by rho nabla phi az minus nabla z a phi rho cap plus nabla z a rho minus nabla rho az phi cap plus 1 by rho nabla rho a phi minus nabla phi a rho z cap. For spherical, it is 1 by r sine theta nabla theta a phi sine theta minus nabla phi a theta r cap plus 1 by r 1 by sine theta nabla phi a r minus nabla r a phi theta cap plus 1 by r nabla r a theta minus nabla theta a r phi cap. The translation of axis is a concept in the geometry and algebra where the coordinate axes are shifted by a certain amount, effectively repositioning the origin of the coordinate system without changing the orientation of the axis. This process simplifies equations or transforms a geometric problem into a more convenient form. How it works. Original coordinates. Let the original coordinate axis have origin O 0, 0 and a point P x, y in the plane. New origin. Assume the axes are translated such that the new origin is at O prime hk, where h and k are the translation values along the x and y axis respectively. Relation between old and new coordinates. If x prime, y prime are the coordinates of the point P in the new system, then x prime equal x minus h, y prime equal y minus k. Effects of translation. Equations of curves. When the axes are translated, the equations of geometric figures like lines, circles, parabolas, etc. are expressed in terms of the new coordinates. Preservation of shape. The shape and size of geometric figures remain unchanged, but their position relative to the new origin changes. The rotation of axis refers to transforming a set of Cartesian coordinate axes x and y into a new set of axes x prime and y prime by rotating them through an angle theta about the origin. This is often used in mathematics and physics to simplify equations or to analyze problems in a new reference frame. Let the original coordinates of a point be x, y. After rotating the axis counterclockwise by an angle theta, the coordinates of the same point in the new coordinate systems are x prime and y prime. The relationship between the old and new coordinates is given by the following equation. X prime equal x cos theta plus y sin theta. Y prime equal minus x sin theta plus y cos theta. Reflection of axis in geometry refers to flipping a figure over a specific axis, such as the x-axis, y-axis, or any other defined line. This transformation produces a mirror image of the original figure. The coordinates of the points in the figure change based on the axis of reflection. Here's how reflection works with respect to the x and y axis. Reflection about the x-axis. The x coordinate remains unchanged. The y coordinate changes its sign. If the original point is x, y, the reflected point is x minus y. Reflection about the y-axis. The y coordinate remains unchanged. The x coordinate changes its sign. If the original point is x, y, the reflected point is minus x, y. Thank you all for your attention.
With this, we have reached the end of our video. Don't forget to give us a thumbs up and leave us a comment if you have any question about the video. Of course, subscribe to our channel. This is it from the team Not Geniuses. Thank you.